Welcome to this course on building an AI-powered automated ordering system using Python and AWS. In this course, we will tackle key challenges in smart logistics by building a full-stack solution for demand forecasting and automated replenishment. The curriculum is structured into 7 main sections. First, in Section 1, we will discuss the objectives of this course and provide an overview of the system architecture within the context of modern supply chain digitalization. From Section 2 through 6, we will build each component of the system step by step. Finally, we will integrate these components to test the system as a unified whole. Let's start with Section 1. Here, we'll define our goals, outline the learning path, review the system architecture, and set up your AWS environment. In the context of our industry, smart logistics or supply chain digitalization refers to solving complex operational challenges using the power of IT and data. The definition of smart logistics is broad. It addresses critical issues such as labor shortages, compliance with new regulations, and the need for financial efficiency. Today, many solutions utilize automation and AI tools to tackle these challenges. In this course, we will move beyond the theory. Through hands-on lectures, we will build a working prototype of an AI-powered inventory and replenishment system to experience these solutions firsthand. Let's talk about inventory management. The core goal here is optimization, maintaining appropriate stock levels to avoid both overstocking and stockouts. Holding excess inventory negatively impacts cash flow by tying up working capital. However, perfect forecasting is difficult. In the real world, we face various constraints and risks, such as weather conditions, damaged goods, and procurement delays. Additionally, every product has a different shelf life, lead time, and demand pattern. In this section, we will explore how to use AI to predict these complex variables, moving away from a reliance on human intuition to a data-driven approach. Now, let me introduce the scenario for this course. We will focus on inventory management, demand forecasting, and automated ordering for an automotive part dealer. Auto dealers sell parts to general customers, but the demand varies significantly by part type. For example, engine oil, wipers, and brake pads are consumables that require regular replacement. For scheduled maintenance services, we must maintain a sufficient stock of these items. On the other hand, suspension parts are replaced much less frequently. Also, just as umbrellas sell when it rains, automotive parts have seasonality, and furthermore, supply chains are complex. Parts from domestic manufacturers may have a lead time of just a few days, whereas imported parts from overseas could take several weeks to arrive. Therefore, we need to hold a higher safety stock for imported items. In our system, we will use machine learning to simulate these complex parameters and optimize our decision-making. Now let's dive into the system architecture. We will implement this entire pipeline on the AWS cloud. Here is the high-level architecture of the system we are going to build. Starting from the left, we use Amazon S3 as our data lake. S3 is a scalable object storage service. We will use it to store historical sales data and weather records. For compute, we will use AWS Lambda. Lambda is a serverless compute service ideal for running lightweight processes. Crucially, Lambda supports container images, so we will deploy our Python application packaged as a Docker container. Inside the Python application, we will use pandas for data manipulation and Scikit-learn, a standard library for machine learning. For the database, we will use Amazon DynamoDB. This is a serverless key-value NoSQL database. Being serverless, it is very cost-effective as you don't pay for idle server time. we will use DynamoDB to store part IDs and the current inventory levels. Next, let's walk through the logic flow implemented in Python. First, the process is triggered by Amazon Event Bridge. The script starts by retrieving the current date. Based on the date, it looks up historical weather patterns. For example, if specific days are historically rainy or humid, we can infer that products like windshield wipers might sell better than usual. Next, we load the necessary data. We fetch the current inventory count from DynamoDB and the historical sales data from S3. Then, we perform the actual demand forecasting. We will call the random forest algorithm from Scikit-learn. By analyzing weather patterns and past sales data, the AI predicts product consumption for the upcoming days. After the prediction, we calculate the required inventory. Note that this step is rule-based, not AI-driven. Here, we apply business logic, such as calculating the safety stock. Finally, we make the ordering decision and update the database. If the projected inventory falls below the reorder point, the system automatically writes a new order record to DynamoDB. Now, let me introduce the concept of serverless computing. First, let's review the standard cloud service models: SaaS, PaaS, and IaaS. SaaS, software as a service, delivers software application over the internet. PaaS, platform as a service, provides a platform, including the OS and middleware for developing applications. IaaS, infrastructure as a service, gives you access to fundamental infrastructure like servers and networking over the internet. Now, serverless computing is a concept that evolves from these models. Serverless doesn't mean there are no servers, it means you don't have to manage them. The cloud provider automates physical servers, virtual machines, scaling, and maintenance. In a serverless environment, developers can focus purely on writing code without worrying about infrastructure management. Let's look at the key benefits of the system we are building. First, it is serverless and event-driven. This means servers don't need to run 24/7. They only run when an event occurs, which significantly reduces fixed costs and maintenance overhead. Second, by offloading infrastructure management to AWS, you don't have to deal with complex server maintenance. This allows you to focus on coding, resulting in much faster development speed. Next, we will prepare the AWS environment. Here I will introduce how to create an account and the tools used. First, let's talk about the tools. AWS provides three fundamental interfaces for managing its services: the Management Console, the CLI, and the SDK. The Management Console, or the console, is a graphical, web-based interface for managing services. It's the main dashboard you use to access all service after creating an account. The CLI, command line interface, is a tool to manage services from a terminal. It uses an access key and a secret access key for authentication. AWS also offers a Cloud Shell, a browser-based CLI in the console that requires no local installation or setup. The SDK, Software Development Kit, is used to integrate services directly into your applications. AWS provides language-specific SDKs such as Python, Go, with libraries for making API calls from your code. Like the CLI, SDKs use an access key and a secret access key for authentication. This is a step to create a root account and IAM user. First, create a new AWS account and then set up IAM user. IAM is a service that manages permission of users in AWS. First, search AWS in your browser and go to the AWS web page. You will see a button in the upper right corner that says Sign into the console and click it. If you already have an account, you can sign in from this page. To create a new account, click Create a new AWS account. Enter your email address to authenticate your email. A verification email will then be sent to that email address. Next, enter your personal information such as address, credit card, phone number, etc. A credit card or debit card is required for your billing even if your billing is zero. If you are not belong to a corporation and use AWS for personal development or just learning, I recommend you to choose the basic plan, which is free of charge. For developer plan and the business plan, you can get support from AWS customer engineers. Once you have completed this process, AWS account will be created successfully. This is a page called Management Console, and this will be the main page when you use the AWS resources from now on. Now, I'm going to configure IAM. The first account that created is called a root user, and it will be a powerful account like administrator with access to your credit card. If the account is compromised, there is a security risk. Therefore, AWS recommends that you create an IAM user and sign in as an IAM user instead of using a root user normally. First, type IAM in the search window above and move to IAM's dashboard. This is the IAM dashboard. In the initial state, root user has MFA is marked with a red triangle. It is recommended that you install the token apps on your smart device, and next time you sign in as a root user, authenticate with MFA. Next, create an IAM user. The next time you sign in as usual, sign in as this IAM user. You should not sign in as the root user except when checking your credit account. Click on User in the left menu, then Add User. Set the username. Check the access key and the password field for the credential type. The access key is used for the API, CLI, and SDK, and the password is used to sign in to the Management Console. Select Attach Existing Policies directly and choose Administrator Access. This will give the IAM user all privileges except credit card access. The tags can be any text you like. Tags allow identification of IAM users. If you create multiple users in the future, you may set the tags to identify each user. After successfully creating a user, be sure to save the access key and the passwords that are displayed. You can also download this in CSV format. When you have done set up IAM, you will return to the console again, and I will briefly introduce you to the structure of the screen. From the menu bar above, you can move to the various management screens. You can return to the top page by clicking AWS logo on your left. Click on Services to see all the services offered by AWS by category. You can also register frequently used services as favorites. Click on the CLI logo to open CloudShell. By doing so, you can manage the command line from within your browser as well. Click on the bell mark to view various notifications. You can find out about events, changes, and incidents for the services you are operating. Click on the question logo to get support. The type of support available depends on the plan. For example, the basic plan allows ticket-based questions about fees, while technical support is available with the paid plans. By clicking on the gear-shaped logo, you can edit the language, the visual mode, and so on. This is a recently added feature. The menu bar configuration may change in the future. Next, click on the pull-down where the region name is listed to navigate to the AWS region. Northern Virginia is selected by default. Basically, by selecting a region that is close to where you want to deploy your services, you can access your resources with low latency. Also, the services deployed and the fees vary slightly by region. Since AWS is a US company, so releases are generally the earliest in the US region and are then after rolled out to other regions. Documentation and other information is also available in English for the latest services and is gradually being translated into other languages. Finally, you can check the account information you have created from the upper right corner of the console screen. Clicking on an organization will take you to the AWS Organization Service page, where you can view information about the organization you belong to. From here, you can also check your service quota and the usage status and so on. If you need to access credit information, you will need to sign out of your IAM user and sign in as the root user. Let me introduce Google Colab. Throughout this course, we will use Google Colab to write and test our Python code. Colab is based on the Jupyter Notebook interface, which provides an interactive coding environment. And this is an industry standard tool used widely in AI and machine learning development. One of the biggest advantages is that essential libraries like Pandas and Scikit-learn come pre-installed. This means there is zero configuration required. You can start coding right away without worrying about setting up your local environment. The best of all, Google Colab is essentially free to use. All you need to get started is a Google account. Next, let's move on to Section 2, Generating Training Data. In this section, we'll set up the environment and resources for our test. Specifically, we'll implement the S3 bucket for storage and the DynamoDB table for our database. Let's look at the automotive parts we are targeting in this scenario. We will focus on wipers and brake pads as they show increased demand under different weather conditions. Naturally, wipers sell best during the rainy season to ensure visibility. They also see high demand in snowy regions. Furthermore, since rubber degrades due to summer heat and the UV rays, many users replace them before the rainy season begins. Brake pads have less distinct seasonality compared to wipers, but they tend to wear out faster in winter conditions. For our synthetic test data, we will apply the following logic. For wipers, we will program the sales figures to increase on rainy days. Since there is always some base demand regardless of the season, we will also add a random value to simulate real-world variability. For brake pads, we will increase the sales volume when the temperature drops. We will also add logic to boost the sales in March, simulating the spring maintenance season. Here are the data fields we will generate. The dataset includes date, product ID, temperature, precipitation flag, humidity, and historical sales. We use temperature, precipitation, and humidity as features to predict sales. Additionally, humidity is used to assess the risk of rust. Generally, if humidity is too high, metal products are at risk of rusting. We will generate this data for a period of 2 years, totaling 730 days. So let's start generating the data using the Google Colab. I am currently on the top of the page of the Google Chrome, and when you open the notebook from here, and you will be directed to this page. And you can enter the command directory here by pressing the Shift+ Enter. You can execute Python code. For example, if you type on the print hello and press Shift+ Enter, the code and its execution results are displayed immediately below, and you can see the result in the interactive format like this. So now let's proceed to actually generate the data from this page. And firstly, we will import the pandas and the NumPy. The pandas and the NumPy are libraries used for the machine learning and data analysis. We write the import pandas as PD. Since these library names are long, it is standard practice to abbreviate them using the names like PD and clicking on the Shift+ Enter. And then no execution result will be displayed for this step. So next, although it is a bit long, I will copy and paste the code directly here, and this function for generating the sample data directly here. This function, let me briefly explain what is inside. The def create mock data is a function defined to create our sample data. It generates the date after the data after the 730 days or 2 years starting from the January 1st, 2023. And down here, the logic is written. And first we generate the weather data. The data is designed to peak around summer and bottom out around winter. And we set the average temperature to about the 50 degrees. And we add 20 degrees to reach a maximum of about 35 degrees. And subtract 20 degrees to reach a minimum about -5 degrees in winter. And this is the logic we are using. And we use the sine function for this. The sine function that oscillates between -1 and 1 by inputting this along with the random value. And we configure the temperature to pick the summer and drop in the winter over a cycle of the roughly 365 days. And the next is the rainy season. And we have the logic where the probability of the rain is higher during the rainy season and in September due to the typhoon. And regarding the humidity, the logic set is higher on the rainy season and also during the summer. And scrolling down, and we have the sales generation logic. The first report, the part A, the wipers, the logic is set so that they sell more during the rainy season, and below that the part B, the brake parts, and we assume these sell in the winter and in March. When the vehicle inspections occurs, we have built the logic accordingly. And finally, the function performs generates the CSV file, and press and the Shift+ Enter to define the function. Okay, and you can find the data generation complete the message here. And the generated data is output as the CSV file, and the name is the training_data.csv file on the file directory on your left. And next, to visualize this data, then we import another library called the matplotlib. I'm going to Shift+ Enter. And we can check the content of the training data.csv file, such as wiper select. And we will use this CSV file as the training data in later chapter. So please download the data, the CSV file to your local directory, and we will save this CSV file to the S3 bucket later on. So that concludes the explanation of how to use the Google Crabble. Next, I'd like to introduce Amazon S3 and Amazon DynamoDB. Let's look back at the system architecture I showed you earlier. In this section, we will focus on the storage layer, S3 for storing historical sales data, and the DynamoDB for hosting our inventory table. Amazon S3 is the most versatile object storage service provided by AWS. In S3, the container where we store files is called a bucket. It offers high durability and virtually unlimited capacity. You don't need to provision storage size in advance. You simply pay for what you use under a pay-as-you-go model. It ensures redundancy by automatically replicating objects across multiple availability zones, which are physically separated locations. S3 covers a wide range of use cases, from storing logs and backups to data lakes. Let me briefly introduce DynamoDB. DynamoDB is a fully managed key-value database. It is one of the most representative database services in AWS and is widely used in the industry. DynamoDB stores data as keys and values. Because key-value databases have a simple structure with paired keys and values, they have the advantage of faster processing compared to general relational databases. DynamoDB has keys and attributes. There are two types of keys, partition key and sort key. The partition key acts like a primary key. Internally, data is distributed based on the partition key, enabling efficient processing. The sort key is used to sort items within that partition. Next, DynamoDB has a concept called capacity modes. There are two pricing modes for table reads and writes, on-demand and provisioned. On-demand means the cost fluctuates based on demand. In other words, if usage increases, the cost increases accordingly. Provisioned reserves the specific usage amount at a fixed price. This means the cost remains constant regardless of whether usage is high or low. You use provisioned capacity mode when capacity can be predicted in advance, and on-demand mode when capacity cannot be predicted. I have prepared a comparison table here. You don't need to memorize the detailed numbers, but please note that you can select the red performance settings for each. Here is the schema for the AutoParts inventory table we will create. We will set the item ID as the partition key, a unique string. Other fields are defined as attributes. Inventory counts and lead times are defined as numbers. Regarding lead time, we assume wipers are sourced from a domestic supplier, so the lead time is set to 3 days. Brake pads are sourced from an overseas supplier, so we set the lead time to 30 days. Regarding categories, we categorize wipers as rubber and brake pads as iron. Since iron is prone to rust, we will use this iron category later in our logic to determine the inventory retention period. So let's start the hands-on for the setting at the Amazon S3 and DynamoDB. And we will proceed to create an S3 bucket and a DynamoDB table. I am currently on the console homepage, and from the search bar, type S3, and let's create an actual S3 bucket. So in the left side menu bar, clicking on the General Purpose Bucket, and click on the Create Bucket, and keep the General Purpose selected, and click on the Create Bucket. And I am currently performing this hands-on in the North Virginia, the US East 1 region, and this hands-on can be performed in any region. But please ensure you consistently use the same single region for all resources, the S3, the DynamoDB, and the Lambda. For the packet name, we're gonna use the old parts, the AI, and since the packet name must be the globally unique, so please add your, for example, your account name or the date after the old parts AI. And for my case, 2025 and January, December, and 25 to ensure you the uniqueness. I will enter the date, leave all the other settings as the default, and click on the create the bucket. And then click on the old parts AI, and then inside the newly created bucket, and we can upload the object from here, and we will upload the sales performance data. So I have uploaded the training data CSV. Then Lambda will access this uploaded data later to use it for training. So once the training data file is uploaded, and going back to the console again, and we're gonna go to the DynamoDB to move on to the DynamoDB, the service dashboard. So this is the DynamoDB's the top page. Then click on the create table, and then we will name the table this time the old, the parts, the inventory, and for the partition key, enter the item ID and select the string for the data type, and leave the sort key and the other setting as default, and ensuring now we are using the on-demand capacity mode, and click on the create the table. So it usually takes about 20 to 30 seconds to the status will be active. And once the state becomes active, click on the table name to enter it. So we will now create the attribute information for this table. Go to the action and click on the create item. So now we are creating this manually for now, and we will enter attribute one by one. Clicking on the add new attribute, first add the current stock as the number. So I'm gonna directly copy and paste here the current stock, and this type to present the current inventory. Then on the same way, add the lead time as number. I'm going to copy and paste the lead underscore type as a number type, and once again the category adds the string type, the category, and then finally add supplier as string. I'm going to copy and paste the supplier directly here. So these are the attributes used for our inventory management, and you can enter the initial values here. For the item name, item ID, we will use the wipers and the brake, and let's name the wiper underscore blade underscore A, and set the initial current stock to the 50, and for read time, and since it is the domestic sourcing, set it the short 3 days, and for imports, we would set it to the 30 days later. And for category, assume the wiper is made of the rubber, so set it to the rubber. And for supplier, enter the something like the Saitama underscore factory, and then create the item. So while you can create the item manually like this, but in reality, the inventory data and the part list contain the huge amount of the data. So it is common to enter them via the command line. Then open the command line icon, and this takes you to the command line interface, the black screen. So let's create the part inventory data using the JSON file from here. The first, use the nano command to create a JSON file and name it the nano initial underscore and the stock.json, and click on the enter. And this opens the editor where you can write the file contents. I will copy and paste the JSON data. I'm going to copy and paste. Okay, inside the old part inventory, and we define the part A, wiper braid A, and the part B as the break disk B. And the JSON contains the inventory info, the suppliers, and the safety stock details. So press the Ctrl plus O and then enter to save, and the Ctrl X to exit. And let's confirm the initial stock, the JSON was created successfully with the LS. Then you can find the initial stock JSON file here. So next, now we will load this JSON data into the DynamoDB table. So I'm gonna copy and paste the code directory, the AWS DynamoDB batch write item, and I'm gonna change the region to US East 1 and North Virginia, and clicking on enter. So it might show the unprocessed item, but this is no problem. But since the wiper braid was already entered manually, so effectively only the new item being added on the updates. So let's verify the contents. Next, the AWS and DynamoDB, the table name, AutoParts inventory, and -- region with the US East 1 region for my case. And you can see the data that was just entered. And if you go back to the table in the console and refresh the screen, so you will see both the break disk B and the wiper braid A are correctly entered. So that concludes the creation of S3 and the DynamoDB. Next, we move on to section 3, demand forecasting with Scikit-learn. This section is the heart of our course, where we will master the workflow of AI and machine learning. In this section, we will cover the fundamental of AI, ML, data preprocessing, and the feature engineering. We will then implement the solution using Scikit-learn and the random forest algorithm. Let's start with the fundamental concepts of AI and machine learning. First, let's clarify the hierarchy of AI categories. Artificial intelligence is a broad concept. Within AI, we have machine learning, which is the technique of learning from data. Inside ML, there is a deep learning, a method inspired by the neural networks of the human brain. Generative AI, which is very popular today, is a specific branch that primarily applies deep learning techniques to create new content. This chart plots data analysis types based on data volume and complexity. Many business professionals are comfortable using spreadsheets like Excel for simple bivariate analysis, processing 2 variables. However, fewer are familiar with multivariate analysis, statistical methods, or the details of machine learning and deep learning. Machine learning is built on complex mathematics and statistics. However, cloud platforms like AWS allow us to execute these advanced tasks easily by abstracting away the infrastructure setup. You don't need to be a math expert to use ML, but understanding the underlying principles is crucial. Without this knowledge, your analysis becomes a black box. In this course, we will balance theory and practice to ensure you understand why it works. Machine learning is one approach to achieving AI. Unlike traditional programming, where humans explicitly write every rule, machine learning allows computers to automatically learn knowledge and patterns from data. While AI is the broad goal of mimicking human intelligence, machine learning is the specific technique of automatically learning patterns from data to construct rules. Let's look at a simple example, ice cream sales. The goal of machine learning is to predict future results using past observational data. Intuitively, sales go up when the temperature is high. In this case, factors like temperature, precipitation, and the wind speed influence the result, which is sales. In ML terminology, the influencing variables are called features. The result is called the label. In statistics, these are often called independent and dependent variables or explanatory and objective variables, but we will use the terms feature and label to align with the standard AWS documentation. The relationship between feature X and the label Y is expressed as a function, y equals x of f. This function is called the model. In machine learning, we estimate this model from past data and evaluate it to improve its accuracy. Traditional computer programs operate on the rules explicitly defined by humans. However, this method fails with the complex problems where rules are hard to define, such as handwriting recognition. Machine learning reverses this approach. Instead of feeding rules, we feed the computer massive amounts of data to let it find the patterns. Through training, the computer constructs its own rules internally. This collection of learned rules is called the model. Once built, we use this model to make predictions on new, unknown data. Here is the standard workflow of machine learning. First, we prepare a dataset and split it into training data and test data. Next, we train the model using the training data. Since there are various algorithms available, we often experiment with multiple models, evaluate their performance, and select the best one through an iterative process. Let's dive deeper into the categories of machine learning. Broadly speaking, machine learning is divided into two main categories. They are supervised learning and unsupervised learning. First, let's look at supervised learning. This approach models the relationship between input data and output data. This is often expressed mathematically as y equals f of x. For example, imagine we have input data such as temperature and precipitation, and output data such as ice cream sales. We use both to build our model. On the other hand, unsupervised learning uses only input data. The goal here is to learn the structures or patterns hidden within the data itself. Common tasks in unsupervised learning include analyzing trends or grouping similar data points together. Supervised learning is further divided into two types, classification and regression. Classification is the task of assigning data to specific categories. And regression, on the other hand, is the task of predicting continuous numerical values. For unsupervised learning, a representative example is the clustering. The clustering is the task of dividing data into groups. It works by splitting input data into clusters that share similar characteristics. I have listed some representative algorithms for these techniques here for your reference. Now, let's focus on supervised learning, as it is the most common approach in machine learning. As the name implies, it proceeds with a teacher. This means it requires correct answer data to learn. In this approach, we use what is called labeled data. A label refers to the correct output or category for a given input. By repeatedly learning from pairs of input data and their corresponding correct labels, the model constructs rules to capture the relationship between the input and the output. Let me explain the mechanism of supervised learning. First, we prepare the input data, which is the information we give to the model. For example, these could be images of dogs and cats. We also prepare the correct labels or the answers. We attach the label dog to dog images and the label cat to cat images. Next, the model receives the input and makes a prediction. It then compares this prediction with the correct label to calculate the error. Please note that in reality, computers cannot see images or hear audio like we do. All data is digitized or converted into numbers before being processed. The model then adjusts its internal parameters to minimize this calculated error. This process of adjustment is what we call learning or training. By repeating this cycle with a vast amount of labeled data, the model gradually becomes smarter and more accurate. As I mentioned, supervised learning is divided into regression and classification. Let's look at them in detail. Regression is the task of predicting continuous numerical values. The output can be any value within an infinite range of possibilities. For instance, sales volume changes based on variables like time, season, weather, and temperature. Predicting that ice cream sales increase as the temperature rises is a regression problem. In the real world, the relationship isn't always a simple proportional one like I equals AX. It can be a complex formula. But regardless of complexity, the problem of finding a mathematical law from a large amount of data is called a regression. Next is classification. This is the task of sorting data into specific categories. Unlike a regression, the output here consists of discrete categories. Common examples include binary classification, like deciding yes or no, or multi-class classification, like identifying whether an image is a dog or a cat. Next is data preprocessing and feature engineering. First, let's understand the machine learning pipeline. This term refers to the end-to-end workflow of a project, starting from data collection, moving to preprocessing, training, evaluation, and finally, model deployment and inference. I will explain the key points you need to consider at each step. First, let's talk about the data itself. In most cases, the raw data we collect cannot be used for machine learning as is. And this is because real-world data is messy. It often contains missing values, noise, or inconsistent formats. Therefore, we must process this data into a suitable format, converting it into a clean dataset that the model can easily digest and learn from. Before we start full-scale preprocessing, we perform exploratory data analysis, or EDA. And this is the activity of understanding your data. Using statistical methods and visualization tools, we explore the dataset's overall structure, patterns, outliers, and relationships between variables. The insights gained from EDA provide the clues we need to decide our strategy for the next steps: data preprocessing and feature engineering. I'm going to explain how ETL process is with an easy example. The table shows a list of names, phone number, email, and age. John Doe is duplicated in the name field. In this case, you can choose whether to allow duplicates or eliminate duplicates. Phone number has to be numeric data type, but some characters are mixed in. There are some blank in email addresses field. Some of the age field contains invalid numbers. When an irregular value is found, you will predefine rules and convert it to an appropriate format. In actual business, raw data often contains missing or irregular values. By processing these kind of data appropriately, the accuracy of data analysis can be improved. Let's continue with data preprocessing. The first is converting categorical data to numbers. Machine learning models can basically only handle numbers, so we need to convert text data into a numerical format. Two common methods are one hot encoding, which represents categories with the 0 or 1, and the label encoding, which converts categories into a simple integer. We also need to scale our features using normalization or standardization. Scale just means the units or range of the numbers. For example, if features have very different scales, like age and annual income, the model might incorrectly think annual income is more important. Normalization scales all values to fit within a 0 to 1 range. Standardization transforms the data to have a mean of 0 and a standard deviation of 1. Next is feature engineering. This is the process where we create new features from the original data to help improve the model's prediction accuracy. For example, we can combine existing features. On an e-commerce site, we could combine number of purchases and the total purchase amount to create a new feature like average purchase value. We can also transform features into a format that's easier for the model to learn. For example, we can extract the day of the week from a date, or bring continuous numbers into categories like low, medium, and high. We also select the most useful features and remove unnecessary ones. This improves the model's training efficiency and helps prevent overfitting, which means the model fits too closely to the training data. After we go through all these steps, the raw data finally becomes learnable. By performing these pre-processing steps properly, I can tell you that we can greatly improve our model's accuracy. In our hands-on session, since our features like date, weather, and product are limited, we will prepare data that is relatively easy to process. Next, I would like to introduce model training and hyperparameters. In the previous chapter, we explained data pre-processing and feature engineering. Now, we move on to model training, where we actually educate the model using that data. In the model training phase, we feed our prepared data into an algorithm. The algorithm learns from it to create a final model capable of performing tasks like prediction or classification. Training refers to the process where we feed data to a machine learning algorithm so it can learn patterns and relationships, ultimately creating the final model. Let's look at this diagram showing the flow of supervised learning. First, we take our prepared dataset and split it into two parts. These are the training data and the test data. Typically, the training data makes up about 80% of the total. The model learns exclusively from this portion. Next, we use the remaining 20%, the test data, to evaluate the performance of the completed model. We perform this evaluation to prevent a situation called author overfitting. Overfitting occurs when a model learns the training data too well. It adapts so closely to the training data that it fails to perform well on new, unseen data like our test set. During the training process, the model uses the training data to calculate the error against the correct labels. It then gradually adjusts its internal parameters to minimize this error. Now let's introduce the Python libraries we will be using in this hands-on session. The first is Pandas. This is a popular open-source library used for data manipulation and analysis. It is specifically optimized for handling tabular data structures called data frames. It allows you to read and process data from various formats like CSV, Excel, and JSON. A data frame is a two-dimensional data structure consisting of rows and columns. It allows you to analyze data stored in a table format similar to Excel or relational databases. By loading data into a data frame structure, processing becomes much more efficient. Next is Scikit-learn. This is the most widely used open-source machine learning library in Python. It provides the necessary algorithms for data analysis and machine learning. It is designed to work seamlessly with other Python libraries like NumPy and SciPy. Scikit-learn offers functions that support the entire machine learning workflow. It is known for being easy to use. Plus, it has extensive documentation and sample code, making it very accessible for learning and implementation. For your reference, I have listed here the common libraries used in the field of data analysis and machine learning. Libraries like Pandas and NumPy are used for data processing. Matplotlib and Seaborn are used for data visualization. Scikit-learn, TensorFlow, and PyTorch cover a wide range of processes, including building and training machine learning models. By importing these Python libraries, we can easily execute complex calculations. One great advantage of using cloud environments like AWS is that these essential libraries are often pre-installed. This means users typically don't need to build an environment from scratch. We will be using these libraries throughout our hands-on session. From here, I will introduce the algorithms we will use in this hands-on session. First, let's talk about decision trees. A decision tree is a method used in data analysis and machine learning. It is a model that classifies or predicts the data step by step based on specific rules. It represents the decision-making process with a structure that looks like the branches and leaves of a tree. Technically, a decision tree consists of nodes and edges, where nodes have a parent-child relationship. For example, imagine trying to solve the problem: will a certain customer buy a product? The decision tree repeats a series of questions to arrive at a final conclusion. In our hands-on session, we have multiple features like weather, date, and humidity. Since these features act as conditional branches affecting the outcome, a decision tree is a suitable choice. One major advantage of decision trees is that their structure is clear. It is easy for humans to understand why the model reached a certain conclusion. On the other hand, they have a disadvantage. They are prone to overfitting. In machine learning, we face two opposing problems: overfitting and underfitting. Overfitting occurs when the model memorizes the data too well, including the specific characteristics and even the noise of the training data. While it performs with high accuracy on the training data, its prediction accuracy drops significantly on new, unknown data. Conversely, underfitting refers to a state where the model is too simple. It fails to capture even the basic pattern or trends of the training data. In this case, prediction accuracy is low for both the training data and new data. Since decision trees are prone to overfitting, we often use a technique called the ensemble learning, which combines multiple decision trees to improve performance. Ensemble learning is a technique where we combine multiple machine learning models to achieve higher prediction accuracy than a single model could achieve alone. By leveraging the strengths of each model to compensate for their weaknesses, we can build a model with higher generalization ability. As a side note, the word ensemble comes from French, meaning playing together or a chorus in music. Just like a choir sounds better than a solo, models often work better together. Let me introduce the representative methods of the ensemble learning. These are bagging, boosting, and stacking. Bagging stands for bootstrap aggregating. In this method, we create multiple learners in parallel and calculate the prediction by taking a majority vote or an average. Boosting involves creating multiple learners sequentially. The model is calculated based on the results of the previous model, gradually improving prediction accuracy. The stacking takes the prediction results of multiple different models and uses them as a new dataset to train a final model. Now let's focus on the random forest. First, the algorithm extracts the random datasets from the sample to create multiple decision trees. Next, it performs calculations using each of these decision trees. The result for each tree is calculated by tracing the data down to the final node. Finally, random forest takes the results from all the decision trees to determine the final prediction. In the case of a classification problem, it takes a majority vote. In the case of a regression problem, like ours, it typically takes the average. By using the results of multiple decision trees, we can prevent the final result from being biased by any single tree. A key feature of random forest is that it can run in parallel for each tree, making calculation time relatively short. Also, even if an individual tree overfits, the impact is diluted when viewed as a whole group. This makes the model robust against overfitting, which is a significant advantage. On the downside, the accuracy can sometimes depend on how the data is sampled, which leads us to the next point. In random forest, you can specify the number of decision trees based on how you sample. In this hands-on session, we will use 100 decision trees to make our predictions. Imagine if we predicted sales based on a single specific date. That day might contain exceptional noise or irregularities. Therefore, by preparing multiple sampling methods, in our case 100 trees, we ensure the model doesn't overrun that noise. Using multiple samples prevents the results from being biased toward specific seasons or specific weather conditions. Next, let's discuss the hyperparameters. These are settings that we, as humans, must set before the training begins. I want to be clear, they are different from the parameters the model learns from the data. The hyperparameters are external settings that control the learning process itself. By finding the optimal hyperparameters, we can get the best possible performance. Common types include the number of epochs, which is how many times the model sees the entire training dataset, and the batch size, which defines how much data the model looks at in a single pass before it updates. The depth of this tree is a hyperparameter. If the tree is too deep, you are very likely to overfit the training data. On the other hand, if the tree is too shallow, it can't capture the data's patterns and it will have low performance. The number of decision trees we choose to combine is another hyperparameter. In this hands-on session, the number of features such as the date, weather, and humidity is relatively small, so a maximum tree depth of 10 is sufficient. On the other hand, since the results are expected to vary depending on the sampling method, we will combine 100 decision trees. Finally, let's talk about tuning methods. To find the best combination of hyperparameters, we have to repeat a process of trial and error. A grid search is a method where we try every possible combination we've listed. A random search tries the random combinations from a range of values. I also want you to know that services like Amazon SageMaker have features that can automatically search for the best combination for you. After we complete the model training and the hyperparameter tuning processes, we have a performance-optimized model. In the next step, we will use the validation data we set aside to fairly evaluate if this model is really usable. Now, let's walk through the actual code implementation. This code represents the computer component we discussed earlier in the system architecture. Here, we will execute the demand forecasting logic, which corresponds to step 3 of our workflow. First, we import the necessary libraries, and we will use pandas, numpy, and scikit-learn. In Python, it is common practice to alias library names to keep the code concise, and for example, we import pandas as a PD. Next is feature engineering. We need to convert the raw date into more meaningful features like a month and a weekday. We assume that environmental features like rain and humidity are already prepared in our dataset, so no further transformation is needed for them. We also define the specific columns we will use as features for the model. Next involves model training. Since the code is quite long, I have split it into functions. We define a function called train models to load the CSV data. Inside this function, we call pre-process features, which executes the data pre-processing steps I just explained. Inside the training loop, we filter the data by product ID to create separate models for wipers and brake pads. Then, we execute training using random forest. We specify 100 decision trees. Note the parameter the random state equals 42. This fixes the starting point of the random number generator. By setting this, we ensure reproducibility, meaning every time you run this code, you get the exact same random sampling and the results. The number 42 itself is arbitrary, but in the programming world, is often used as a nod to the sci-fi novel The Hitchhiker's Guide to the Galaxy, where 42 is the answer to the ultimate question of life, the universe, and everything. Finally, we call model.fit to train the model. Now we move to the prediction phase. This depends on the lead time. First, we generate a list of future dates. For example, if the lead time is 3 days, we look at tomorrow, the day after, and the day after that. We then loop through these days using a for loop to calculate the daily demand. Here, we perform a prediction based on past temperature, humidity, and weather data. For temperature, we use a sine wave function. This allows us to automatically generate a realistic-looking temperature data for future dates where we don't have historical records. We set the annual average temperature to 15 degrees. We set the fluctuation range to 20. This simulates a summer peak of around 35 degrees and a winter low of around -5 degrees. The sine wave is a periodic function adjusted to complete one cycle over 365 days. For humidity, we assume it is high, like 80% during the summer months from June to August. For rain, we use a simple logic. If humidity is high, we flag it as rain. In a real production environment, you would use a real weather forecast API, but for this hands-on session, we are simulating the data within the code. Next, we execute the inference. This calculates the total demand based on the simulated weather and the specific lead time. For wipers, we predict 3 days of demand. For brakes, we predict 30 days. Finally, we write a test script to verify that the program runs correctly on Google Colab. The expected output should show logical trends. Lower predicted values when rain is scarce, and higher predicted values during peak demand season, such as winter for brake pads. So let's do the hands-on running AI logic on Google Colab. So let's continue from where we left off in the previous notebook execution. And previously, we generate the training data.csv file within the environment, and we will be using this test data for the next steps. And with that in mind, so let's proceed with the coding. Now I'm gonna copy and paste the AI logic directly into the Google Chrome. I'm going to copy and paste it. And this is the exact same logic which I just introduced in the previous section. And first we handle the time and the date acquisition, and we also perform the data pre-processing in this section, and then we train the data with the Lambda forecast, and in section 3 that we include the prediction for the temperature and humidity and the rain, and at the bottom we execute the inference. So now press Shift plus Enter. Okay, at this stage no result will be displayed yet. And once defined, move to the cell below, and we will actually train the model using the train underscore model function, and with our CSV data, the training data.csv file, and clicking on the Shift plus the Enter. The training should finish immediately, and please confirm that the training has been executed for the both the wiper and the brake. So the one point of the caution, with the free version of the Google Cloud, the runtime might reset after a period of the inactivity, causing the file to be disappear. And if you cannot find the CSV file, please rerun the code from the previous section to generate the CSV file again. And scrolling down to the bottom, and since the training is complete, and we will now execute the prediction using the code with this. So click on the Shift plus Enter. So as you see, for the wiper, the 92.7, and for the brake, the 584.7 unit is predicted. For the wiper, we simulate a date in June, the rainy season, with a short read time of 3 days. The AI predicted a high demand due to the rain, and resulting in about 90 units. And for the brake, we simulate the winter scenario with a long read time of 30 days. And since it sums up the demand for the whole month during the peak season, the prediction is much larger, the 584 unit. So this concludes the testing for this section. Next is section 4, implementing order decision logic. In this section, we will use Python to implement the logic for safety stock and order decisions. We will also test the Python code we create to ensure it works as expected. The core logic we are implementing here covers inventory calculation and the order decision process. Later in the course, we will deploy this Python code to AWS Lambda, but first, we will execute and verify it in Cloud Shell. Before we code, let me explain the concept of the reorder point using a practical example. This image illustrates the concept of the reorder point. Imagine the vertical axis represents the inventory level, and the horizontal axis represents the date. As we ship products daily, the inventory level gradually decreases. When the inventory touches the reorder point line, the system triggers a new order. Because there is a procurement lag time, the ordered goods do not arrive immediately. During this wait, inventory continues to decrease at a constant rate. Finally, at the exact moment the inventory level reaches the safety stock line, the ordered goods arrive, replenishing our stock. In this hands-on scenario, daily consumption fluctuates according to the season. As introduced in the previous section, consumption is calculated using our machine learning logic. Lead time is set to 3 days for domestic sourcing and 30 days for overseas sourcing. The safety stock is basically set to 14 days. However, we will include an anti-rust logic. If the humidity is high, we reduce it to 7 days to minimize the rust risk. First, let's look at the example of wipers. Since wipers are domestically sourced parts, the procurement lead time is 3 days. Suppose our AI predicts a daily consumption of 20 units based on past dates and weather data. Since safety stock is set to 14 days, that serves as a baseline of 280 units. However, remember that actual demand fluctuates even during these 14 days. The reorder point is calculated as 340 units, considering both the safety stock and the consumption during lead time. Therefore, the system must place an order when the logical inventory drops below 340 units. Next is the example of brake pads. Since brake pads are sourced from overseas, the lead time is 30 days. Suppose the AI predicts daily consumption of 5 units based on past trends, with a safety stock of 14 days. The baseline is 70 units. The reorder point is calculated as 220 units, combining safety stock and the lead time demand. Therefore, we place an order when logical inventory drops below 220 units. Finally, let's look at the brake example during seasons that require rust prevention. Since brake pads contain iron, they are vulnerable to rust. We will add logic to reduce safety stock to 7 days during the rainy season when humidity exceeds 70%. As before, since they are overseas sourced, lead time is 30 days. Assume the predicted daily consumption is 5 units. If humidity reaches 70%, the system automatically reduces safety stock to 7 days. This makes it 35 units. Consequently, the reorder point becomes 185 units. This logic ensures we hold less inventory than usual during the high humidity rainy season to maintain quality. We will now build the safety stock and order decision logic using Python. I have omitted the parts that duplicate the previous section. Here, we define the calculations for safety stock, average daily consumption, and the inventory levels as we just discussed. Next is the logic to adjust the safety stock based on humidity. Normally, safety stock is set to 14 days. However, for iron products, specifically brake pads, if the humidity is 70% or higher, we configure the system to hold only 7 days of safety stock. So let's start the hands-on for running the business logic simulation. We will continue the hands-on session on the Google Cloud, continuing from the previous section, and we will proceed using the cells below. I will copy and paste the Python code, explain the lecture directly here, and first we will define the business logic. And this is the calculate the safety stock, and this logic indicates normally the stock is 14 days, but the logic dictates that if the product is made of the iron and humidity is 70 or higher, then we reduce the safety stock by 7 days to prevent the rust. Clicking on the click shift %, and at this stage, we have only defined the function, so nothing is returned yet. So next we will simulate the order decision. I'm going to copy and paste the code directly here. And the Lambda simulation function is a bit long. It references the item ID and the current stock and the lead time, and it also utilizes the AI consumption model that we introduced in the previous section. And we have that also includes the formulas for the order decision and the inventory calculation here. So the press Shift plus Enter. Okay. Again, since we only define the function, then no calculation result returns. So next we will input the test data in JSON format. Okay. And this is the test data. In the production environment, we would ultimately use the DynamoDB, but since we haven't connected to the DynamoDB yet, we are using the JSON as the test data, and we have entered the current stock and the read time for the wiper, and we also listed the stock and the read time for the brake here. And we have prepared 3 test cases. The test case 1, the wipers, we simulate the rainy season where the rain is predicted. And for the brake, we have prepared 2 patterns, and the case 2 is a normal spring season, and the case 3 is the rainy season where the rust prevention measures are necessary. And then when we execute this, so the result returned immediately. And you should verify the safety stock standard, the project, the remaining stock, and the order. The recommendations are displayed correctly for case 1, case 2, and case 3. And in particular, you can see in the case 3 that the logic to shorten the safety stock during the rainy season has been correctly reflected. So this concludes the test for this section. Next, we move on to section 5, deployment to Docker and AWS Lambda. In this section, we will first introduce Docker containers and AWS Lambda, explaining why we chose this specific technology stack. Then, we will cover permission management using IAM, followed by the actual implementation on AWS. Let's start with Docker and Lambda. This is the system architecture I showed you at the beginning. In the previous sections, we used Google Colab as our test environment. We confirmed via unit tests that the Python logic works correctly using test data. Next, we will deploy this logic as a functional application. We will deploy it as a container image to Lambda, which will serve as our production environment. First, let me explain the reason behind this architectural choice by introducing Lambda. Lambda is an event-driven serverless computing service. Event-driven means the service executes triggered by specific events. It is not always running. Also, you are billed only while the function is executing. Since it is serverless, there is no need for infrastructure layer management. Lambda automatically executes code in response to events while integrating with various resources. The services that execute functions in the cloud are called the function as a service. It supports various programming languages such as Java, Python, and Go. It can integrate with a wide variety of AWS services. Lambda supports a wide range of use cases. For example, it can execute functions triggered by HTTP requests in integration with API Gateway, execute functions triggered by S3 data uploads, or execute functions on a fixed schedule. This is the lifecycle of the Lambda execution environment. Skipping strict technical details, the Lambda function lifecycle consists broadly of init, invoke, and shutdown. In the first invocation, Lambda downloads the code, starts the runtime, and performs initialization. In the next invoke phase, the function runs to process the event. When processing is complete and it remains idle for a certain period, the execution environment is destroyed. Since Lambda is an event-triggered service, it does not run continuously. It launches triggered by specific events such as external triggers or schedules. By default, the init phase is limited to complete within 10 seconds. If it exceeds 10 seconds, it will be retried. The timeout is a maximum of 15 minutes. When many requests are sent simultaneously, Lambda launches execution environments to perform parallel processing. The number of concurrent executions per region is limited to 1000 by default. If requests exceed this, an error occurs due to throttling. If the number of requests increases and the function fails to operate due to reaching the Lambda concurrency limit, you need to request a quota increase. According to AWS official documentation, it is possible to raise this limit to tens of thousands. In this system, we are using AWS Lambda, but AWS offers many other computing services. I have summarized the representative ones here. To reiterate, Lambda is a serverless service and does not run continuously. It runs only when there is an event. Also, since you are built only during execution, it offers excellent cost performance. On the other hand, a virtual server services run continuously and incur fixed costs. For our system, the calculation time is a matter of seconds, and the data volume is sufficiently small, so Lambda is the optimal service. Order processing is executed via API each time, and the scale of each calculation is small. In reality, there are systems that calculate inventory once every 24 hours. In systems for large enterprise factories or retail stores, large-scale batch processing is often executed at night. For massive processing, where a single runtime exceeds 15 minutes, other services should be considered. Next, let's discuss Lambda quotas. A quota is the limit on the resources you can use. Regarding computing, there are limits on concurrent executions, uploadable zip file size, and ENIs per VPC. These quotas can often be increased by submitting a request. For function configuration and execution, there are limits on memory, timeout, layers, and ephemeral storage. These have default and maximum values. In Lambda, you cannot configure the CPU directly. CPU power is allocated proportionally to the memory you select. Also, Lambda has a strict timeout limit. It can run for a maximum of 900 seconds, 15 minutes. In other words, long-running processes exceeding 900 seconds are not possible, so you must use other services for large-scale data processing. There are two main ways to deploy application code to Lambda: uploading a zipped file or using a container image. With the zip method, the system must unpack the code before running the program. If the file is large, the unpacking process takes time, so very large files cannot be used. With the container method, the image is loaded from Amazon ECR, a container repository. Container technology utilizes techniques like layer caching and lazy loading internally. Layer caching allows the system to reuse code that hasn't changed. Therefore, it can start up quickly even if the image size is large. As I explained, this system uses libraries for machine learning. When we use libraries like Pandas and Scikit-learn, dependent libraries like Scipy are also installed. These libraries contain a large number of compiled binary files. As a result, the file size becomes significant. As a rough estimate, it can exceed 300 megabytes. It is worth noting that Python machine learning libraries have become bloated in recent years, making them larger than before. If we try to install these via command and zip them, we risk hitting Lambda's quota limits. Therefore, we will adopt the method of deploying as a container. Next, let's discuss permission management using IAM, identity and access management. IAM is a service that manages access permission to resources and the accounts that access them. Using IAM allows for fine-grained access control, defining who can perform what action on which service. This enhances security across the entire environment. As mentioned during account creation, a root user is created initially, but typically you sign in as an IAM user. An IAM user holds permissions to execute specific actions on specific resources. And furthermore, IAM can set permissions not only for users, but also for resources. For example, you can set permissions to allow a specific Lambda function to execute or be restricted from specific actions on a specific DynamoDB table. This enables security designs such as the principle of least privilege. Next, let's discuss permission management using IAM. In our system, the application deployed on Lambda needs to interact with S3 and DynamoDB. Therefore, we need to grant a specific permission to the Lambda function. First, for S3, we need to grant read access so the function can retrieve the necessary files. Next, for DynamoDB, since it stores our inventory data, we must grant both read and write access. Finally, we also need to grant permission to write the execution logs internally for monitoring purposes. Next, we will move on to the actual implementation in the AWS environment. Here is the workflow for our implementation. First, we will create the container definition file. Next, we will configure ECR and IAM. Then, we will build and push the container image. Finally, we will create and configure the Lambda function. Let me introduce a few key points about the configuration before we start. First involves creating the container definition file. Here, we list the necessary libraries. Boto3 is the Python library used to interact with AWS resources, while the others are for our AI logic. One point of caution: for compatibility reasons, you may need to specify the exact versions for some libraries. I have summarized the details in the troubleshooting section. Next, we create the Docker file. The Docker file serves as the blueprint for the container. For this course, we will use an official AWS-based image. Inside the Docker file, we configure the Python environment, install libraries, copy the source code, and set the startup command. Next is the build and push process. First, we need to perform a login so that our Docker client can access ECR. Next, we run the Docker build. We will create the image directly on CloudShell. Please note that building Scikit-learn takes time, so expect this process to take a few minutes. Once the build is complete, we apply a destination tag to the created image and upload it to ECR. Lambda will then load this image file from ECR to execute our application. Next, let's look at the Lambda function code. I will skip the explanation of the AI and the business logics that we covered in the previous sessions. First, we import the necessary libraries and set up constants. We also load the AI module we created previously. Additionally, we configure DynamoDB to retrieve the current inventory and set the S3 path to retrieve historical sales data. Here, within the newly added functions, we handle the necessary data exchange with S3 and the DynamoDB. In the function getCurrentStock, we retrieve inventory and the product information from DynamoDB. In the function downloadTrainingData, we retrieve the past training data from S3. So let's proceed with the final implementation starting from the AWS console top page. And first we will configure the ECR, the type E, CR, the Elastic Container Registry, to the service page. Then from the left side menu bar, you can see the repository, and click on the Create a New Repository here. And you can upload the Docker file directly here, but this time we will execute this using the command line via the Cloud Shell. Click on the Cloud Shell and open the command line interface. First, we will create the directory and the Python file. Firstly, I'm gonna make the directory with the old parts AI make directory, and moving on to this directory cd old parts AI. And you can upload the file via the action menu, but we will create them directly here using the nano command. I will copy and paste the code directory in the Cloud Shell directory. nano, nano, and the first Python file is AI underscore logic.py, and this is a Python file that handles the training and future projection logic. Clicking on the enter, and I'm going to copy and paste the directory here and press the code and write out to the Ctrl+O and enter and exit to Ctrl+X. Okay, so on the same way that we will create the nano and lambda underscore the function.py, and this is the main function that lambda will execute directly. So enter, and I'm going to paste the code directly here. And then the important thing is that please update the DynamoDB table and the bucket name. Please update with the bucket name. For my case, bucket name is the old parts AI with the random suffix. And then press the Ctrl-O to write out, enter, and the Ctrl-X to exit. Okay. Next, we will create the requirement.txt file. nano, the requirements.txt, in the same way. And here we define the necessary library, the pandas, numpy, scikit-learn, and the bot3, and Ctrl-O, enter, and the Ctrl-X to exit. Okay, next, finally, the Docker file, the paste the contents on the same way, nano, and then Docker file, and copy and paste the file, Ctrl-O, and enter, and Ctrl-X to exit. So we have created the 4 necessary files. So let's check the ls command to see confirm they are saved correctly. So next we will create the ECR repository via the command line. Then I'm going to copy and paste the command. The AWS ECR create repository, and the repository name is the old part AI, and the region, for my case, US East 1 North Virginia, and clicking on the repository name, the old part AI. So going back to the ECR page, clicking on the repository, and confirm that the repository named the AutoParts AI has been created here. Again, going back to the Cloud Shell. So we will now build a container. The first we need to log in, and we will retrieve the account ID and specify the region, and the US East one for my case. Okay, you can find the login succeed. You might see the warning that the password is not encrypted, but login was succeeded, so we can ignore it. So next execute the build command with the docker the build the -t AutoParts AI, and then click on the enter. And this will take a few minutes, so I will pause the recording here. So the build completed in about 2 minutes. So next we will tag the image and push it to the ECR repository. So this also takes a little time, so we will wait. So the push finished in about 20 or 30 seconds, and returning to the console ECR page, and since we pushed the AutoParts AI, so check inside the repository, and you should see that the image has been uploaded successfully. So now that the container image is ready, so next let's create the Lambda function, and going to the top page, the console screen, and type Lambda to go to the Lambda service page. And this is the dashboard of the Lambda. On your left menu bar in the function, and click on the create function. And this time, since we are using the container image, select the container image and name the function with the order function. And for the image block, browse the image and select the ECR repository and choose the images with the tag latest, and click on the select image. So for the execution role in the permission tab, okay, then we're going to create the new role with the basic Lambda permission, and we will add permission for DynamoDB and S3 later. Click on the create function. The Lambda function should be created immediately. Since it was created from the image, you cannot view the code directly here. And we need to adjust a few settings to go to the configuration tab and select the general configuration. And by default, the memory is 128 megabytes and the timeout is 3 seconds, and this is too small for our need. And since we are running the AI logic, let's increase the memory to the 512, for example, and the timeout to the 30 seconds. So save these changes. And next go to the permissions, and you can see the permission role with the order function role. So click on and go to the IAM page. Okay. By default, the role only has the basic execution role, and we need to add permission so this Lambda can access the S3 and the DynamoDB. Click on the add permission and then attach policy. And for S3, since we only need the data, so we need to read the data. Select the S3 read only access. And for DynamoDB, since we will perform both read and write, so select the DynamoDB full access. Click on the add permission. So as you see, the policies have been attached. So this completes the configuration for ECR, Lambda, and IAM, and that concludes this hands-on section. Next, we move on to section 6, scenario testing. Since we successfully deployed our function to Lambda in the previous section, we will now conduct actual tests to ensure everything works. For this testing phase, we have prepared 4 different scenarios. These scenarios follow the same logic we discussed in section 4 regarding order decision logic. First, for wipers, we expect higher sales before the rainy season. Next, regarding brake pads, since the safety stock strategy changes based on humidity, we will include test cases for both high humidity and low humidity conditions. Finally, since brake pads tend to sell better in winter, we will include a specific winter season case. Let's recap the overall calculation flow using test scenario 1 as our base. First, we provide the input values, specifically the date and the weather information. We will input this directly into the Lambda test console in JSON format. Internally, the system will retrieve the current inventory from DynamoDB and execute the AI consumption prediction. View the order decision logic for this specific scenario. Since wipers are domestically sourced, the procurement lead time is 3 days. Because the lead time is short, the required inventory level is relatively low. Suppose our AI predicts a daily consumption of 30 units based on the past date and the weather data. With the safety stock setting of 14 days, the safety stock volume becomes 420 units. The reorder point, considering safety stock and the lead time, is calculated as 510 units. Therefore, the system must place an order if the logical inventory drops below 510 units. Since the current inventory is only 50 units, we expect the system to display a message recommending an order of roughly 460 units. We will execute all test scenarios keeping this logic in mind. Now let's actually execute a test from the old order function page in the Lambda console. Open the test tab on the Lambda function page, and we will create the test case here. Click on the create a new event. For the first case, we will create the test for the wipers. Name the event with the test 01, the wiper lane, and you can leave other settings as default. In the JSON editors below, I'm going to copy and paste the JSON, event JSON, and clicking on the save and clicking on the test. So the calculation should be immediately, but for the first time, it takes a little bit longer time for the initialization. So let's look at the calculation result. Open your detail and scrolling down to and here, and then the recommended order is about 110. The consumption is slightly lower than I expect for the peak season. And this is because the date I entered, the May 20th, is not quite deep into the rainy season yet. So the logic didn't trigger the maximum rain prediction. So if we were to change the date, for example, to June 20th, and the save and run again, and open the detail. So the something's like the 470 units, and this confirms the logic workings as expected. So As a side note, the recommended order is displayed as the integer, while the consumption forecast is a decimal. Since we cannot order fractional units in the really inventory management, the calculation round up to the nearest full number. So next, let's create the new event. Create a new event, and then in the same way, we will look at the test 2 for the break test for the break, and then I'm going to copy and paste the JSON code. Okay, and clicking on the save and clicking on the test. Okay, similarly, it runs in about the 2 seconds, and just like the previous test, it shows the current stock and the consumption forecast, and the recommended order is 111. The result is displayed correctly. So let's proceed with the remaining 2 tests in the exact same way. Next is the test. Click on the create a new event and the test case number 3, and then copy and paste the test 3. Okay, since the June is a rainy season and we assume the heavy rain, the save and click on the test. Okay, so because of the high humidity, you can see the last alert warning. The logic reduces the safety stock from the 14 days to 7 days to prevent the rust. The result is also expected. For the final pattern, let's look at the break in the winter. Choose the create a new event with a test case for number 4, and I'm going to copy and paste the JSON and click on the save and click on the execute the test. Okay, the test returned immediately on the same way, and you can see the recommended order quantity. Okay, this quantity has increasing the significantly. It was around the 100 units before, but the backend logic assumed break consumption increases dramatically in winter due to the road freezing, and therefore the recommended order quantity is much higher. So since we have confirmed the expected behavior for all cases, and we will conclude the integration testing. Next, we move to section 7, conclusion and future steps. First, at the beginning of this course, we learned about the general challenges of inventory management. In inventory management, it is crucial to maintain optimal inventory levels while avoiding both excess stock and stockouts. We explored how we can use AI to predict demand rather than relying solely on human intuition. Next, we covered AWS services and Python logic. The services we used are serverless, meaning there are no servers running continuously, making them cost optimal. Additionally, AWS automatically handles the scaling as the volume of requests fluctuates. This significantly optimizes your operational overhead. We also implemented machine learning and business logic using Python. In this course, we called the random forest algorithm from Scikit-learn to perform demand prediction. We also wrote the code for the safety stock and the reorder point logic. Finally, we experienced the entire end-to-end workflow following the machine learning pipeline, from data collection, pre-processing, and training to deployment and inference. During this process, we also configured the hyperparameters. through this course, you have learned the implementation of inventory management, machine learning, and programming. With that, I would like to conclude the main explanation of this course. Thank you very much for watching.